Okay, so this first video is about sketching polynomials, which we have started to work on from Algebra 2. So we're going to continue what we hopefully already remember from Algebra 2. So things to remember. Polynomials have graphs that are smooth and continuous, meaning there's no corners, there's no breaks. So an example of something, would look beautiful like that, right? Maybe something that looks like a W. Those are all great polynomials. Again, I'm not drawing an x-axis or a y-axis. These would be non-examples, right? So these are like no's, right? So an absolute value, that's a no. We'll get to things called wholes, right? So anything that like kind of asks me to lift up my pencil. Piecewise functions, right? They are technically functions, but they're not polynomials, right? So something like this. So this is yes, and these are no. Okay, so the first thing we want to talk about is the end behavior, right? So graphs kind of have two types of end behaviors. They're either going in the same direction or they're going in opposite directions. Okay, and so it all forms into this long polynomial. And basically, what this reads, you don't have to. This is just the general form, comes straight from your book, and it just has your highest degree. So if this was a power of 4, then it'd be 4, 3, 2, 1, and then 0. So a sub naught is always your constant term. And then these are just coefficients, which we will talk about later. General form tells us that our a of n cannot equal 0. And if we think about the reason why is because if I plug this in as a 0, then my largest degree goes away. So basically what we want to do is we want to figure out kind of what's going to happen. So what happens if my n is odd, right? So those are like your 3s, 5s, 7s, so forth and so on. There's two characteristics, right? Your characteristics will either have your a of n greater than 0, meaning that your a of n is positive, or your a of n is going to be less than 0, so -1, -2, -3, aka your a of n is going to be negative. So these are kind of like what's happening with your graphs. Notice that your graphs are kind of going in opposite directions for both of these, and I just drew a dashed curve because, again, I don't know what's actually happening. So how do I describe my behavior? There's a new notation that I want you guys to start using, right? So if I just quickly drew kind of an x-axis and a y-axis, so to speak, and I don't really care where my x-axis and y-axis lie, right? Ask yourself, as my x's are increasing to infinity, kind of where's my arrow going? It's going up, right? So instead of saying it's going up, right, or it goes to the right, things like that, we want to use this notation. And it says as x, and I draw an arrow saying it's going to infinity. So as x is approaching infinity, what's happening to my output? What's happening to my y? Well, my f of x is also going to my infinity. So really what this tells me is this is my end of my domain, right? So my domain is ending at infinity. Where's the end of my range really going? It's also going to infinity. So if you're looking at this side, as my x is getting smaller and smaller and smaller, where do you notice the arrow is pointing? It's pointing down, right? So I can say as x approaches negative infinity, my f of x is approaching also negative infinity, right? In case you can't see that negative sign. So, so this would be considered the left side of the equation, or the left side of the function, and this would be considered the right side of the function, right? And so we want to make sure that we put both what's happening to the x's and to our outputs, our f of x's, right? So, so we could do the same thing over here, right? This time I'm not going to try to visualize where you think the f of x or the x-axis and the y-axis are going. So as my x's are kind of decreasing, right? So as x approaches negative infinity, where do you notice my arrow is going? It is going up. So my f of x is going to positive infinity. So that means the opposite's true over here. So as x approaches a positive infinity, where's my f of x going? It's going to negative infinity. So they're going in opposite directions. So that's kind of what your a of n is. If you forget, think of the smallest n value. That's odd. It's a 1. right? Which is your linear line. So if you have a positive slope, your positive slope kind of looks like this. If you have a negative slope, your line would have these two end behaviors. So you can always rely back on what you already know. Okay? When your n is even, so these are your 2s, 4s, 6s, 8s, things like that, right? Your a of n is going to be greater than 0. Notice that you're both facing up. So how I can describe my n behavior is that as x approaches negative infinity, my f of x is approaching a positive infinity, right? It's just going up. And then on this side, as x is getting larger and larger to infinity, my f of x is also going up, right? So again, you can kind of relate back to even. Smallest even number is a 2. So you think about your parabola when your when your a value was positive, right? Your parabola opened up, so it's opening up. When your n value, or sorry, your a value was negative, so like a negative x squared, your parabola is kind of opening down, right? So I can say as x approaches negative infinity, my f of x is approaching negative infinity, and as x approaches a positive infinity, f of x is approaching negative infinity, right? So my outputs are always, they're always the same. So again, it just tells us like n behavior and things like that. Okay, so the other thing that we want to talk about is not only with our n behaviors, is what's happening with our zeros, right? How else do we graph? We have to know our zeros. So we have what's known as the real zeros of polynomial functions. And you're going to want to pause it and write this down. So what this says is that if I have a polynomial and it has an a value and it's a real number, right? So we haven't talked about imaginary numbers in this class, so this is something I can physically count to, then all of these 4 things are equivalent to each other. Okay, 1 and 2 look basically the same. So x is equal to a, so x is equal to a number. I can either call that an answer, right? I can call that a solution, or I can call it a 0. Okay, so you are going to hear both, right? It's a solution when you think of it as I set my equation equal to 0. You're solving for for what your x value should be, right? It's also known as an x-intercept. So again, I can, if it's a 0 of a function, I'm going to graph that along my x-intercept. And I want to make sure that I can write it as an x-intercept. So it'd be a comma 0. Now, I can also write it as a factor, and this is something that we're going to come back to in the next video on synthetic and long division. So if I set my factor, because again, when we're solving factors, right, we set it equal to 0, and if I add a to both sides, boom, I'm right up to number 2, or I'm right up to number 1. So if I just subtract a to both sides, I got x minus a. So these are your real zeros of polynomial functions. The other thing we want to talk about before we start graphing is what happens when we have repeated zeros. So there's 3 scenarios that are going to come up in this class. Okay, so if you have a 0 that's just repeated once, so you don't see it but one time, the graph just crosses the x-axis normally at that a, so at that x-intercept. If you see it, if you see it repeated twice, so I see the number 2 written 2 times, then what's going to happen is it's going to like bounce off of it, so it's not going to cross the x-axis, and I'll show you an example of what those look like. And then if it's repeated thrice, right, fancy word for 3 times, right, what it's going to happen is it's going to cross the x-axis as a cubic, right, and we want to make sure for our cubic that it does go cubic at that 0, right? I don't want to see the cubic above the 0, below the 0, just like I don't want to see the bounce, right? What's going to happen with the bounce is it's going to look, here's your 0 and it's going to bounce right off. I don't want to see the bounce above that point or below that point. I want to see it on that point, right? Crossing it just normally, it's just going to boom like that. And there's your normal cross, okay? So what we want to do is we have a couple different examples. They're all a little bit different from each other, okay? And they're all about finding the zeros and graphing and describing the end behavior. So here's our very first example. So you might want to take a moment and copy it down. So I'm going to find the zeros of this problem, and then I'm going to graph and I'm going to describe the the end behavior. So the first thing I want to do is I'm going to take this equation, I'm going to set it equal to 0. So x cubed minus 6x squared minus 16x Again, these are going to be pretty easy finding the zeros. They'll be factorable. So we're going to factor out the x. So we get x squared minus 6x minus 16. Okay, again, if you don't know what multiplies to 16 and adds to a negative 6, it's an 8 and a 2. The 8 being negative and the 2 being positive, so this becomes x is equal to, sorry, x times x minus 8 and x plus 2, right? So everything, right, is set equal to 0, so I can take my factors and set them equal to 0. So I can set x is equal to 0, I can set x minus 8 equal to 0, I can set x plus 2 equal to 0. So I have my zeros. So I have 0, 8, and negative 2. Boom, right there. Okay. Again, we're going to talk about this when we come back. Notice that there's 3 zeros. And notice what my highest degree is, power of 3. Right? You'll always have that many zeros with the degree number. All right. So do any of my zeros repeat? No. Perfect. So now I just want to make some tick marks. So I've got zeros right here. That's perfect. So 1, 2 negatively over there. And then I got to go to 8. 1, 2, 3, 4, 5, 6, 7, 8. Oh, just made it. Perfect. So what's happening with my highest degree? It's a power of 3. So that means that it is odd. Notice that my first term is a positive 1. So if we think back, the end behaviors kind of look something like this. So they're going to go in opposite directions. It's going to end going up, right? So I know I'm going to start down here and end over here. So I always like to draw arrows of kind of where I'm supposed to start and where I'm supposed to end. And I'm just going to go straight through all my zeros. I do not care how high or how low you go. And you drop. Boom. Right? So again, I can erase these random arrows that I originally drew. And we're done. So describe this end behavior. So as my x is getting larger and larger, or sorry, increasingly smaller and smaller, I should say, negative infinity, where is my f of x going? Well, it's going down, right? It's going down to negative infinity. As my x gets larger and larger, so as x approaches a positive infinity, again, this is the introduction of kind of, this will be the introduction of like calculus and limits and things going to infinity. Where does your graph end up going? It's going up and it's going to a positive infinity. That's all I need you to do when I ask you to label your end behavior. Okay, let's try another one. All right, so I want to sketch this graph again. We'll talk about describing the end behaviors. Notice this one's already known as factored form. This was in factored form while this problem was written as a general form. So this one does not have binomials where this one does. So all you want to do is set them all equal to each other. So this is like saying x minus 1 2 times, x plus 3 3 times, right? I don't need you guys to multiply the binomials out. Please do not do that. Right, so if I set that, my zeros are as followed. I got 0, so don't forget that x. This will give me a 1 twice. I will get negative 3 3 times, and then I'll get a negative 1 2 times. So I do have a multiplicity of 2, and I have a multiplicity of 3 right there. So I want to pay attention. So I'll make a little tick mark at 0, and then I'm going to go to 1, and I go to negative 1, negative 2, negative 3, boom, boom. Okay, so when I have multiplicities and they're at different numbers, I like to put little b or c next to what I want to do. So I know that there's going to be a bounce at b at 1, so put a little b there. I know that there's a cubic through negative 3, so I'm put a little cube sign right there. Now on this one's going to be a little bit more challenging to figure out what my end behavior is. So notice that I don't have any negative numbers in front of this x. So I do know that my a of n is greater than 0. And then all you want to do is you want to add up those exponents. So I got a 1, 2, so total I have 3. 3 plus 3 gives me 6, and then I have a power of 1 right there. So my degree is a 7th power. So again, it's positive, it's 7th, so I know I'm going to go in opposite directions one more time. Okay, and so what's happening? I'm going to start down here. I'm going to go through cubically. So it goes cubically, almost looks like it goes horizontally through that cube. And then through negative 3, then 0, or no, sorry, -1, I should say, first. So -1, and I got to be quick. It's going to come up through 0 and then up quick through 1, but I'm going to bounce off and boom, take off. So erase my original arrows. Don't have to worry about that. Describe your end behavior. So what's happening as x is approaching -infinity? Where is your arrow pointing? It's pointing down. So f of x is going towards -infinity. As your x increasingly gets larger and larger, where does your output go? It increasingly gets larger and larger. Okay, let's try another one. Okay, what happens if I ask you to write it in factored form and then sketch it, right? So, if you only know your zeros, there are kind of different things that we can do, right? We are assuming that your a of n is going to be positive, so let's assume for right now your a of n is going to be greater than 0, right? So if I write it in factored form, that would be as if I just set x equal to 3, x is equal to 2, x is equal to -1, and then move the 3, the 2, the -1 over. So I'm going to, pencil broke again, x minus 3, and then I get an x minus 2, and then I get an x plus 1. Now, think about this way. I had 2 -1s, so that means I'm going to put a little squared sign on top of that. So, boom. Okay, what do I notice? There's a bounce at -1. So there's my -1, put a little b next to that. I got it at 2, 1, 2, and then I have one more at 3, power 2, 3, 4, so this is a 4th degree. So that means I'm opening upward, something like that. So start near your bounce, that's your first 0, so you're going to bounce, and then go through your point, and then up. Right, erase your original arrows. And then, since we're sketching, let's also describe our end behavior. So as x is getting smaller and smaller, going towards -infinity, where is your arrow pointing? It is pointing up towards positive infinity. Same thing on this side. As x approaches a positive infinity, where's your outputs going? Towards positive infinity. Right? So again, just another type of problem that you guys are going to see. The last type would be to write it in factored form based on this graph. Okay, and again, this is all you know. So you're going to take some information. We don't know the stretch factor, so we don't know if our a of n is going to be larger than the number 1 or smaller than -1, right? So the first thing I would do is I would look at your zeros. So I notice that I have a 0 here, here, and here. So I have zeros at the number 1, 2, 3, 4. So the number 4. I have a 0 at -2, and then I have a 0 at -2, 3, 4, 5. So -5. What's happening at -5? There's a little bounce, right? What's happening at the -2? There's a cubic. So what else do I notice? I notice that the arrows are pointing down, right? So again, think back to when your arrows point down. N is going to be even, so we know you're going to have an even power, but your a of n is going to be less than 0. Again, you're just going to pick a number. So when I write it in factored form, right, there will be x minus 4. Don't have to worry about any exponents. Become x plus 2, it's cubic, so there should be a 3 on top of that. Be an x plus 5, it's a bounce, so there should be a 2 on that. So notice 2 plus 3 gives you 5, 5 plus 1 gives you 6. So I do have a 6th degree polynomial. But right now, notice that my leading coefficient, right, in front of all my binomials is a positive number. But notice that these arrows are pointing down. So I want my a of n to be less than 0. Right? So just pick a number, any number. I'm going to pick -1. Boom. Now I've written an equation that goes with this graph, right? Because again, I don't really know how low this goes and how high that goes. Taking us back to chapter 1, our relative minimum point, relative maximum point. So I don't really know if that should be a -1 or if it should be, say, -3 and things like that. So there are multiple answers for this type of problem. Okay, so again, we can describe the end behavior if we wanted to, just for fun, right? So as x is approaching -infinity, where's my f of x going? It's approaching positive infinity, right? As my x approaches positive infinity, where's my f of x going, right? Again, my output, again, it's going down, negative infinity. So I want you to really get into that habit of writing your end behaviors like that. Okay? And again, any questions or concerns, email me, and hopefully I will be able to get back to you as soon as I can, and just follow the worksheet. All right?